Hello, here's another batch of practice questions in quantum physics. So starting with, in atomic physics, electron energies are often stated in electron volts. Define the electron volt and state its value in joule. So we've got then the electron volt. This is the energy gained by an electron. Energy gained by an electron when it is accelerated through a potential difference of 1 volt. By an electron accelerated through PD of 1 volt. So that means then, because remember our volts is joules per coulomb, so we multiply 1 volt by the charge of an electron and then we're going to get joules. So that means it's going to be equal to 1.6 times 10 to the minus 19 joules. Right, that's part A. B, an electron is accelerated from rest through a potential difference of 300 volts. Calculate the final kinetic energy of the electron in electron volts and in joules. Right, well, in electron volts, it will just be 300 electron volts. That's the point of it all, isn't it? You know, 1 electron volt is if we accelerate through 1 volt. So if we go through 300 volts, we're going to get 300 electron volts. And then for joules, we just need to multiply by the 1.6 times 10 to the minus 19. So that'd be 3, 1.6 is 4.8. And then we've got 100 on there to make that 10 to the minus 17 joules. So that is good. Show that the final speed of the electron is around about that. So that is going to be equal to a half mv squared. So our v squared is going to be, well, we double that to 9.6 times 10 to the minus 17. And then we have to divide by 9.1 times 10 to the minus 31. Do the square roots. Obviously, I'm going to need to calculate for that one, which is going to come out to a 10 to the 7, because when we square root that bit, it's going to be a little bit over 10 to the 7, isn't it? Here we go, 1.03 times 10 to the 7 meters per second. So we'll just have to put that, they've only given us the one significant figure there, so we'll just say 1 times 10 to the 7 meters per second, one significant figure. Right, so far so good. Explain what is meant by the de Broglie wavelength of an electron. So this is the wavelength of the wave nature of an electron. So we can start off by saying that. So the de Broglie wavelength is the wavelength of the wave nature of an electron. Now you might want to put in a little more than that of wave nature of an electron. So you might want to add in something like as evident or as observed when electrons are diffracted by a crystal lattice or something like that. Right, a crystal lattice. So at least you're sort of fleshing it out a little bit more to show how you can actually observe this de Broglie wavelength. Calculate de Broglie wavelength of the electron in B. So that is Planck constant divided by momentum. So they've given us the, we've got the final speed. So everything's there, just fine to type in, isn't it? So sticking this in the calculator, 6.63 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31, mass of the electron, and then the 1.03 times 10 to the 7 for that speed that we calculated. So working that out in the calculator, we're getting 7.066 times 10 to the minus 11 meters. So 7 times 10 to the minus 11 meters to one significant figure, seeing as that's all they've given us in this question. Right, that was a nice, easy starter question. Next one up, in 1927, it was shown by experiment that electrons can produce a diffraction pattern. Explain the meaning of the term diffraction. Right, so this is going back to our wave section then. So this is the spreading out of a wave after it passes through a gap. So I can't be bothered to write that out because he's done that loads of times in the wave section. But yeah, the spreading out of a wave after it passes through a gap. State the condition necessary for electrons to produce observable diffraction when passing through matter, e.g. a thin sheet of graphite in an evacuated chamber. So we want the de Broglie wavelength of the electron to be comparable, so a similar size to the atomic spacing in the matter that they're passing through. So that's what we're after there. It's the same thing that we always want with diffraction, isn't it? You want to have the wavelengths being similar to the gap, and then we can produce observable diffraction. That's what it says in the question. So there we go. Show that the speed of an electron with that de Broglie wavelength is that. Okay, so, well, we used this on the previous question. That's our definition. So if we want to get speed out of this, splitting momentum into mass times velocity. So then our velocity is going to be h over m lambda. So we just need to, again, type these numbers in. So I'll just say them as I put them in the calculator. So we got 6.63 times 10 to the minus 34 for our Planck constant. Then we've got the 9.11 times 10 to the minus 31 for the mass of the electron, and then they've given us that de Broglie wavelength of 1.2 times 10 to the minus 10. That is coming out then at 6.06 times 10 to the 6 meters per second, which is pretty much what they want. Okay, then part C. The electrons in B are accelerated to a speed, to that speed using an electron gun. Okay, that's our electron gun. Calculate the potential difference across the DC supply between the cathode and the anode. Okay, so we've got a conservation of energy thing going on here. So our kinetic energy of the electron, the half mv squared, is coming from our E times V. So that's a capital V there for the PD. That's our joules per coulomb multiplied by coulombs. So the PD that we want, a capital V, is then going to be, so we've got the mass of the electron, 9.11 times 10 to the minus 31, multiplied by, so this speed squared, so 36 times 10 to the 12. And then we've got to divide by 2 lots of the charge on the electron, so 3.2 times 10 to the minus 19. So, yeah, what's that going to come out as then? So, actually, all these cancel, all these 10s, don't we? We've got 10 to the 31, 10 to the 31. So they're all just disappearing. This isn't going to be far off 100 by the look of it. Or thereabouts. So what have we got? So we got 10 times 36. Yeah, so it is going to be close to that. Anyway, the calculator is telling me 102 volts. So 100 volts to 2 significant figures they've ramped it up to on this question. Suggest why in an electron gun the cathode is connected to the negative terminal of the supply rather than the positive terminal. Right, well, because we want to accelerate the electrons away from the cathode and towards the anode. But yeah, because we want to accelerate electrons away from cathode and towards anode. Otherwise, they're not going to go anywhere, are they? If that's going to be the positive terminal, then yeah, they're just going to stay where they are. Right, okay, so that was another fairly straightforward affair, that one. Next up, we've got a laser here used to form precision welded joints in titanium. To form one such joint, it is first necessary to increase the temperature of the titanium to its melting point. Okay, so we're heating up this joint. And okay, right. The photon beam from the laser is focused on the shaded volume of the joint and is converted into thermal energy in the titanium. The wavelength of the photons is that. Show that the energy of a photon in the beam is that number of joules. So, well, we know that our energy is Planck's constant times the frequency, which is Planck's constant times speed of light divided by the wavelength. So 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by, what was the wavelength they gave us? 1.1 times 10 to the minus 6. So calculate a time, and that is giving us 1.8. Well, as they've said in the question, 1.8 times 10 to the minus 19. There we go. Photons are emitted from the laser at a constant rate of that. Estimate the time taken to raise the temperature of the shaded volume to melting point using all of that data down there. So, right, let's start with our power then. So our power, so this is our joules per second we want on this. So we've got that number of joules per photon, that number of photons per second. So if we multiply those together, then we're going to get our power. So sticking those in, I mean, you can see the tens are going to cancel. So we're going to end up with 1.8 multiplied by 6.3, which is 11.4 watts. So, right, that's our power. Then we're going to need the mass of titanium. Mass of titanium. So we need to do our, what have they given us here? Oh, they've given us the density and they've given us the volume. So we just need to multiply those together. So density times volume. So that is 4.5 times 8.1. And then we're going to have a 10 to the minus 9 on all of that. So 4.5 times 8.1 times 10 to the minus 9. I'm going to save the calculator until I'm putting all the numbers together, I think, on this. Our change in temperature, so that's going up from 20 to 1700, so that's 1680. So on all of this then, we're going to have our power times time is going to be equal to the, what have we got? Where's the heat capacity? I haven't used that yet. I'm doing an MC delta T on this. So 520, that's our heat capacity, multiplied by our mass, which is this 4.5 times 8.1 times 10 to the minus 9, and then times our change in temperature, which is 1680. So E equals MC delta T. We're just going back to our thermodynamics days on all of this. So right now I can type all of this in, so I just didn't bother doing it earlier on. Saves me going to the calculator just the once. And T, when I divide by the 11.4, comes out at 2.8 times 10 to the minus 3 seconds. Right, so that's pretty quick. But it is a small joint, so yeah, you'd expect that to be a small number, and so it is. There must be more to this, I think. Right, here we go. Part C. In practice, it takes a longer time to reach the melting point. State and explain 2 factors that will increase the time taken. And these are ones where you can't just say, oh, heat loss to the surroundings. That's just not specific enough, and the mark schemes will never give you marks if you just say something like that. So we want 2 things, state and explain. So we can say conduction of energy out of the shaded zone. Out of shaded zone. So at least we've said there that we're saying that energy is being conducted out. We're given an actual method of energy transfer, and that will increase the time taken. Then we've got 2. The other one we could have scattering, I suppose, reflection or scattering. Either one's going to be fine. Of laser beam from the surface of the metal. So because both of those are going to give us energy loss, but at least we're saying how the loss is happening. We're not just saying, oh, there are losses. You know, that just isn't really good enough just to say that. So 2 specific cases there. Right, last part. To complete the weld, more photons must be focused on the joint. During this final stage, the temperature remains constant. Explain why this is to be expected. Right, again, this is all our thermodynamic stuff. So this is our latent heat of fusion, because remember, we're melting this, so we're going from solid to liquid. So this is our latent heat of fusion rather than the latent heat of vaporization. So latent heat of fusion, i.e. potential energy change, potential energy change, rather than, so, or not, the increase in temperature. And then you can increase in temperature, which you can then contrast by saying, well, that would be a kinetic energy change. So that is why there is no difference in temperature. Right, they were 3 really quick questions, but nice. I mean, you can see, again, the quantum physics questions, because there's not that much to the section that we actually cover in quantum physics before we go to university. They will often mix it in with other topics. So they've mixed it in here with thermodynamics. They mix it in a lot with electromagnetism and circuits and such like for accelerating those electrons, because otherwise they're just too noddy-ish really in the calculations that need to be done. So yeah, mixing them together is just, they're ripe for it really.